Assalamu alaikum. Welcome to your today's lecture in Principles of Computer Networks. Today we'll discuss the transport layer. In this lecture, we'll have an introduction to the transport layer. We'll study sockets, TCP, and UDP protocols. The transport layer is an end-to-end layer. That means the nodes, intermediate nodes on the subnet are not included, does not participate in the transport layer protocols. Only the end hosts, the sender and the receiver. With other layers, transport layer protocols send data in a sequence of packets called segments. The transport layer sends the segments to the internet layer where it's encapsulated in IP packets, and it's sent to the host to network layer where it's encapsulated into frames and sent in the physical media. Transport layer provides efficient, reliable, and cost-effective services to its users. The users are usually processes in the application layer. It makes use of the services that's provided by the network layer. And the part of the transport layer that is responsible of providing the service and making use of network layer services is called transport entity. It's hardware and or software within the transport layer, and it does the work. It might be a part of the operating system kernel or a separate user process or a library package bound to the network application, or it can be purely physical as a part of the network interface card. The transport entity provides the service to the application layer through the transport address, that is called port, and it's a part of the application transport interface, and it uses the network layer through the network address. The transport layer data unit is sent between the transport entity on the host to the transport entity in the second host. As you can see, the transport layer transport entity can be connected to a single transport address or to multiple transport layer addresses. That's where the multiplexing happens. There are two types of transport layer services, connection-oriented and connection-less services. There are similarities between the transport layer services and the network layer services. The connection-oriented service is similar to the connection-oriented service in the network, where the connection is established, data transferred, and the connection is released. It has addressing and it has flow control. The connection-less transport services is also similar to connection-less network services. So why is the redundancy? Because there are a difference between transport layer services and network layer services. The transport code runs entirely on the user's machine, while the network layer mostly runs on the routers, which are not controlled by the user. The network layer has problems losing packets, routers crashing, congestion in the network. The transport layer improves the quality of service of the network layer. The transport services are more reliable than network services, and application programmers can write code according to the standard of transport layer primitives. And these programs can be run on top of different networks without any regard to the type of network that the program is running on. The transport layer provides some operations to application programs through transport layer service interfaces. Each service has its own interface. Transport services are similar to network services. The difference is that the network services are unreliable because they run on the real networks, while the transport services improves real networks, providing reliability. Network services are for network developers, while transport services are for application developers. The network layer provides communication between two hosts. The transport layer provides communication between two processes on different hosts. A process is a program in execution, and there can be multiple processes communicating between two hosts. For example, an FTP process can be communicating, and there is also a telenet session and email session between the two hosts, the same two hosts. The transport layer provides a way to multiplex and demultiplex connections between various processes. It provides the multiplexing by adding addresses to each segment, indicating which source and destination processes are communicating. These addresses are called port numbers. Usually the communication is identified by a table of 5: sending port, sending IP address, destination port, destination IP address, transport layer protocol. This will uniquely identify process-to-process connection on the internet. The transport layer data unit, that's called segments, is encapsulated in the IP packet. And the IP packet is encapsulated in the frame, in the data link frame, where the transport layer data unit with its header is considered a payload for the IP packet, and the IP packet, including the transport layer data unit, are considered a payload for the frame. There are many transport layer service primitives. Here we inspect the most common ones. Listen is a block system call for the process waiting for a process to try to connect. There is no send packets. Connect, this is actively attempting to make a connection between two processes. A connection request is sent. Then after the connection is established, there will be send system call for sending information. And on the other side, there will be a receive system call, where it's a blocking system call until the data packets arrived. After finishing the session of sending data and receiving data, one of the sides will want to release the connection, so it will send a disconnection request that will activate the disconnect system call. Listen is local, while connect is local and remote. Send will be sending the connection number, the buffer size, and the bytes of data that are sent. Receive will receive with the connection number, the buffer size, and the bytes that the receiver is willing to receive. Disconnect will use only the connection number to disconnect. As we can see here, the establishment of the connection starts from the sender, where the sender will send a connection request to the receiver. On the receiver, there are multiple processes, as we have said. They can be an email server, a web server, a telenet server, and a file transfer server. All these can be present on the receiver. Instead of making all these processes listening all the time to the incoming ports, a process called process server is listening on their behalf as a proxy, and it listens to multiple ports at the same time. When the connection request comes for a certain port, the process server will call the intended server to connect with the user. The protocol stack for the transport layer consists of the application, the socket interface that we are going to inspect shortly, to create new endpoints to allocate table space for it within the transport layer. Then the transport layer to identify the applications given a port number, the network layer to identify the node, giving it an IP address, and the data link layer framing all this information and using the network interface card to identify the network identified by network interface card address. What is a socket? A socket is a software interface designed to communicate between user programs, and TCP/IP protocol stack. It's implemented in set of libraries, functions, and function calls. A socket is a data structure inside a program. Both client and server programs communicate via pair of sockets. The socket framework consists of 5 layers. First, we have the application program in the user space, the socket layer itself in the kernel space. Then comes the transport layer protocols, TCP or UDP. Then comes the IP protocol. Lastly, the physical network represented by the physical network driver. There are several socket domains families. The most important ones are Internet domain sockets implemented via IP addresses and port numbers, Unix domain sockets implemented via named pipes, Novell IPX sockets, and AppleTalk sockets. The socket types are stream sockets used by TCP protocol connection-oriented service, socket diagram used by UDP protocol connectionless service, and raw sockets used for testing. The communication between TCP client server is very simple. The server creates a socket, binds a port number to this socket, and then listen to this port number for incoming connections. The clients create a socket, send a connection request to the server accepts the connection request, and then the client writes to the connection, the server reads from the connection, loops until the server writes to the connection, the client reads from the connection, and this will be a loop until the communication finished. Then the communication will be closed. On the server side, there will be the system calls are socket initiation to create a socket, bind to register port to the system, listen to establish a client connection, accept to accept the client connection, read and write to read, write, and data, then close to shut down the connection. On the client side, there is initiation for the socket, connection request, read and write until the data is finished, then close to shut down the connection. The connectionless clients and servers create socket using socket diagram instead of socket stream. The connectionless services don't listen or accept. They usually don't call connect at all. Since connectionless services lack sustained connection, several methods are available to allow you to specify destination address with every call. With every call, there would be send to socket number, buffer size, buffer length, flags to address, and receive from socket number, buffer length, flags from address. On the server side, there will be socket initiation, creating a socket, bind to bind the port number to the socket, then receive from and send to data, and then close to shut down the connection. On the client side, there will be creation for a socket, sending and receiving data, shutting down the connection. The transmission control protocol is the protocol that provides connection-oriented services for the transport layer in the TCP/IP protocol stack. It's a connection-oriented, full duplex protocol, reliable transport, flow control, congestion control. The UDP, on the other hand, is a connectionless protocol that does not provide any of these services. The TCP creates a connection between source and destination. where it receives the data from application process that write to TCP buffer. The TCP send segments, these are transport layer data units for TCP, and it reached the destination where it's received in the TCP buffer, and then it's passed to the application layer process that is on the sender side. TCP converts the unreliable best effort services for IP into reliable services. It ensures that each segment is delivered correctly, only once, and in order. In order to do this, the TCP uses the same methods that have been used in the data link layer. The TCP numbers each segment and uses ARQ protocol to recover lost segments. Some TCP versions uses go back N, and others uses selective repeat. However, there are few important differences between transport layer and data link layer. At data link layer, we have viewed that the ARQ protocol being operated between two nodes connected in a point-to-point link, while at the transport layer, the protocol is implemented between two hosts connected over a network. That leads to the packets can arrive out of order, and packets may also be stored in a buffer in the network and arrive much later. The round trip time will change for different connections, and connection establishment is much more complicated. The TCP header consists of 16 bits source port, 16 bits destination port, 32 bits sequence number, 32 bits acknowledgement number, TCP header length, flags, window size, checksum for the whole header and data, urgent pointer to indicate this data is urgent, it shouldn't be buffered. There are options from 0 to 32 bits words, and there is data which is optional. There can be only header sent if this is an acknowledgement without data. This is an example for a TCP segment where the first two are the sender port number and the destination port number, the acknowledgement number and the segment number, the timestamp is an optional header field, and the data is sent after that. The connection establishment in TCP is what we call a three-way handshake, where a sync request is sent to the server. The server will reply with a sync request and an acknowledgement. Then the receiver, which is the client, will reply back with the acknowledgement to the sync request sent by the server. The connection closing is a little bit complicated, where the client sends finish segment to the server. The server will acknowledge the finished segment and sends a finished segment of its own. Then the receiver, the client, will send an acknowledgement that it has received the finished segment from the server, and it will wait for some time to ensure that all the packets and acknowledgements are dead, and then it closes connection. As we have said, the client receives finish reply with acknowledgement, enters wait time, will respond with an acknowledgement to the finish segment from the server. The server receives the acknowledgement and the connection is closed. This can be also modified a little bit to handle simultaneous finishes, where both sides want to close the connection at the same time. The transmission policy for TCP is implemented through sliding window protocol. The application will send, here we have a 4K sliding window, 4K buffer at the receiver side. The application sends 2K with sequence 0. It's in the buffer, and the acknowledgement is sent back for 2048 with Windows size, current size is 2048. The application sends another 2K, so the window is full. The receiver will send an acknowledgement for the 469 and 96, all of them. With window size 0, the receiver will stop not sending any other segments until the receiver consumes 2K from the buffer, and now there is 2K free. It will send an acknowledgement with the same a segment with the same acknowledgement number with the new window size. Then the receiver will start resending data. In a network, it's often desirable to limit the rate in which the source can send traffic to the destination. That's because we don't want to overwhelm the network with a very high rate of send segments that can fill up the buffers within the network, leading to a long delays and eventually packets being dropped. Moreover, upon packets being dropped, there will be retransmissions that will congest the network more. If the source is not regulated, this can lead to what is known as congestion collapse, where the network will collapse and there will be very few packets delivered to the destination. There is two different factors can limit the rate which the source send data: the inability of the destination to accept new data, and that's to say the window is full. So here the flow will be controlled by sending the new window size, and the sender will regulate itself to the new window size. The number of packets within the subnet techniques that addresses this are referred to as congestion control, which is different than flow control. It controls the number of packets within the subnet rather than the ones are sent to the receiver regarding its window size. The flow control and the congestion control can be addressed at the transport layer, but they are addressed in other layers, as we have seen in network layer and in data link layer 2. For example, the data link layer protocols perform flow control for each link, and some congestion control approaches are done in the network layer. Both flow control and congestion control are parts of the TCP. The congestion collapse happens when the number of packets sent is too large for the network to manage. Usually, the more packets sent, the more packets are received, until we reach a point where the network is saturated. Then the network will be congested and the number of packets received will drop while the number of packets sent is increasing. Congestion control may be addressed in both network level and transport layer. In the network layer, there are possible approaches, including packet dropping. When the buffer is full, the router can drop packets, but if not coupled with another technique, this can lead to greater congestion because of the retransmissions. Packet scheduling, certain scheduling policies helps in avoiding congestion. In particular, scheduling help to isolate users that transmitting at high rate. Dynamic routing, when a link becomes congested, the router will redirect the traffic to another route which is not congested. But if the sender continues sending packets in a high rate, this will actually makes every single link congested, and this can lead to instabilities. Another way is admission control or traffic policing, where this allows only connection if the network can handle them and make sure that admitted sessions don't send too high rate. Only useful in connection-oriented networks, because in connection-less networks, every packet is routed independently. Another approach that is used by both network and transport layers is rate control. This refers to a technique where the source rate is explicitly controlled based on feedback from either the network or the receiver. For example, if the routers have experienced congestion, they can send a choke packet to the sender, where the sender should lower its rate. These approaches can be classified either congestion avoidance, if they try to prevent congestion from occurring, or congestion recovery, if they allow the congestion to happen and then they react to it. In general, it's better to prevent than to recover. Different networks have used different combination of all these approaches. Traditionally, the rate control at the transport layer has been used in the internet, but new approaches beginning to be used and incorporated with some of the transport layer techniques discussed above. The TCP implements end-to-end congestion control. It detects congestion via acknowledgement from the sliding window, used for providing reliable services. When the source times out before receiving an acknowledgement, most likely the reason is there is a congestion. TCP uses this to indicate the congestion and slows down the transmission rate. The TCP controls transmission rate of a source by varying the window size from the receiver. The difference between flow control and congestion control can be illustrated as follows. If we imagine a tab which controls the transmission rate, the flow control happens when the sender have more capacity than the receiver. So it happens so that the sender cannot overwhelm this receiver with the small capacity with data. But the congestion control happens when the receiver has large capacity, but the network does not have large capacity and the traffic is choked in the network. For this not to happen, the slow start algorithm is used, where there is a congestion control window. For starters, start with the value 1, that's 1 kilobyte. After each acknowledgement, the window is increased by 1. First, after this first acknowledgement, 2 packets are sent. After the 2 packets are acknowledged, 4 packets are sent. After the 4 packets are acknowledged, 16 packets are sent, and so forth. If a loss was detected, the congestion window will be decreased by half. As we can see here, the algorithm is very simple. Until loss, after every packet acknowledged, the congestion window is increased. In case of loss, the threshold will be decreased by half, and depending on loss type, there will be selective acknowledgement or fast transmission and fast transmission. And the congestion window will remain half. The course grain timeout will happen where the congestion window equals 1, and you will start the slow start from the beginning. For selective acknowledgement to be used, they have to be agreed upon from the beginning of the connection. The sender will send selective acknowledgement permitted to the receiver, and the receiver will understand that it can send selective acknowledgement. Selective acknowledgement are sent when packets are lost, indicating which packets were lost by sending the acknowledgement for the next packets received. The coarse grain timeout happens when the sender does not receive an acknowledgement after a period of time. This event is called retransmission timeout. Retransmission timeout value based on estimated round trip time. The RTT is adjusted over time using the following formula, where the RTT equals 1 minus x times the previous RTT plus x multiplied by a sample RTT. X is typically 0.1. This was first used in TCP Tahoe version. Fast retransmission happens when the receiver expects packet n but gets n plus 1. As in the example, the receiver is expecting packet 3000, but it gets packet 4000, packet 5000, and packet 6000. It will send immediately acknowledgements for 3000s repeatedly. After the sender receives three consecutive acknowledgement for 3000, it will infer that the 3000 packet was lost and it will resend it. It's called fast retransmission because it doesn't need to wait for the whole round trip time. And this is introduced in TCP. TCP connection management can be modeled using the following states. Closed, when there is no connection active or pending. Listen, when the server is waiting for incoming call. Sync received, when a connection request arrived for the server, waiting for acknowledgement. Sync sent, when the server sends back the acknowledgement along with a sync request. Established, when the connection is established and data transfers begin. Fin wait 1 is when the application said it has finished. Fin wait 2 is when the other side agreed to release the connection. Timed wait is waiting for all packets to die off. Closing, when both sides try to close the connection simultaneously. Close wait is when the other side initiates a release. And last acknowledgement, waiting for all packets to die off. As we can see here, the start is with closed, then a connection sync request is sent. When the connection sync request is received, an acknowledgement is sent, and by the listening server, then an sync acknowledgement is sent, while upon its receiving, the connection is established. When the data transfer finished, there will be finished segment sent and acknowledged. Another finished segment is sent from the server to the client. Then the client will perform close wait, waiting for all the packets to die off. Then it will send last acknowledgement, closing the connection. The server will perform finished wait 1, then perform finished wait 2, and wait for all the segments to die off. Then it will close the connection. The other transport layer protocol is User Datagram Protocol, UDP. It's an unreliable protocol It's connectionless, no connection is established, no flow control, no congestion control. It's used for applications where prompt delivery is more important than accurate delivery, such as voice over IP, video conferencing, and so forth. It's just like postal services where you drop your mail in the mailbox and you hope for the best it will reach the destination with no guarantees. It's a datagram protocol. That means it doesn't establish connection to the other machine before sending data. It takes data from application, packs it in UDP packets, hand it to the IP layer. The packets are then sent on the wire with the best effort that IP protocol provides, and that's the end. There is no way to guarantee that the packets will reach the destination and whether it will reach it in order and whether it will reach it correct or not. The main function for UDP is multiplexing capability on the top of IP. It multiplexes several processes streams into single IP stream. They are distinguished just like TCP with port number and UDP protocol identifier and IP address, the same 5 tuples as in TCP. The UDP header consists of port number for the source, port number for the destination, the UDP length for the whole header and body, and the UDP checksum. The checksum here is optional. It's calculated for both header and data and some parts of the IP header too. It's not processed by the UDP. It's passed for the application with error flag to deal with it. Your reading assignment for this week is section 6.2, 6.3 from chapter 6, Computer Networks by Andrew Stewart Tannenbaum, chapter 3, Computer Networks, a top-down approach by Kurz and Ross. There is no writing assignment. See you on Tuesday, inshallah.